Hey, welcome to this second part of exponential log functions. We've done all the hardest work in examining the mathematics around these functions. Now let's use them in modelling and some practical work here now. So you can see from these diagrams here, it's like the bacteria problem we were talking about in the last section. We're looking at data and trying to fit a model, here we are, a graph or a model, a formula to the set of data. And here are our little data points in here. There they are. And we're going to examine how well a model fits and can we actually gather empirical data and then fit a model. And there's all sorts of ones. Look at this one down here and over here. These are interesting examples. They're all basically an exponential function with some variations. And this is going to be exciting stuff to see how we can play with the formula for the exponential function. And, we might be using y's and t's, but generally in this section we're going to be using contextual symbols, if you like. So they're going to mean something, not being y and x land, which we usually use to analyse a function, but we're going to put it in the context of maybe population growth with time, and that's going to be a very important part in this section, to really make sure when you're doing a problem that you contextualise it. Come out of y and x land off the calculator and make sure you put it in the context of a population, or I don't know what this might be, mass or something like that in the particular context. So now this y equals, a e to the x or something like that is going to be the basis of our work, but we're going to extend it and we're going to get into other functions, more complicated exponentials than this, and we're going to go out of y's and x's into a context. So keep that in mind as we move from more theoretical maths to applying it now in a context. You hear that word context, you're going to hear it a lot because it's very important in this work. Okay, let's come down and have a look at what we're going to be doing. Oh yeah, I told you already. We're going to be doing some modelling, and it's called here exponential surge and logistic modelling. What? What's that? Surge and logistic. Well, let's have a look. We'll start off with a simple exponential function. Here it is here, y equals ae to bt, and we're starting off with the theory of it, so it's just y and x land. Oh, we've got a t in there, so we've got a little bit of a context. We're looking at y varying with time here, I guess. Well, I haven't defined it here down here. Yes, I have. The independent variable t is usually time, and we're going to change the y's to represent some context. Now, first of all, what we're going to do is have a positive b value in there. So it's ae to some positive power. What's that mean? Well, if we've got e to the bt, t is going to vary. If b is a positive, we've got a positive base e raised to a positive times t. So it's going to increase because effectively e to the b, you could think of it like this, all to the t. This is definitely a number greater than 1, isn't it? So it's going to be an increasing function. Over here, if b is less than 0, let's have a look at it. E to the bt, and this is a negative. This would mean this is e to the b all to the t, and b is a negative. What does a negative power mean? It's 1 on e to a positive here. Put it underneath, it'll be a positive power now. Okay, so this would mean it's going to be a fraction. It'll be a fraction raised to a power. So that's why this is going to give a decreasing function. Let's just watch that, because it's got a common base e, but if e's raised to a negative power here, it creates that fraction. Okay, if b is negative. Alright, so watch out for that. and we're going to use those two as our basic models for exponential growth. So increasing function over here again, something like growth, e.g. the example I gave you in the last presentation, bacterial growth, decreasing function, right, radioactive decay, you might say, radioactive decay, an isotope gives off radiation, particles that is, and then takes a different form, decays, and so on. So we have those two basic models from your previous study. So just watch now, let's summarise what's happening. Because you've got an A in front, here it is here, when you put B, or T is naught, BT will be naught, E to the naught would be 1, and so A is the value that the function will start at for a t or an independent variable of 0. So that's going to be down here, the y-intercept. We've done this before in prior study. And of course, if b is greater than 0, the function is increasing. B is less than 0, the function is decreasing, because it's a negative power, remember, which implies 1 over, we've got a fraction raised to a power, so it's going to decrease. And here, the independent variable is usually time, in the context that we're going to be working. Okay, not always, but in the context we're going to be working, it would generally be. Okay, so let's go down and have a look at some of the other possible models we might use. Oh, here's a new one for you. A surge function. Here it is up here. A surge function. Why is it called that? Well, let's have a look at the old surgy here. Surges, doesn't it? As time goes by, the independent variable there, which we're still calling y because we haven't come into the full context yet, surges up. It's coming up quickly, reaches a max and then slowly goes down. All right, so some current surges can be modelled like this, but probably the most common one is when you have medicinal doses of drugs and stuff in dentistry or medicine, and there's initial rapid increase and then a slower decay to 0. And we're going to be looking at what's the, I suppose, a level here that you need for pain killing, so that the surgeon can operate between these times without pain to the patient. So this is pretty important modelling, isn't it? To realise the effectiveness of that pain-killing drug and the consequences of that. Okay, so I'm just going to scrub some of this out now, because I want you to have a good look at the characteristics of this function. So what would you be interested in? Well, you'd be interested in the time when this is a maximum. Now, the maximum pain killing here, so is that at this time here. How would you do that? Let's just revise that. So if y equals at e to the neg bt, this point is when dy by dt is naught, isn't it? So if you're in an exam or test situation where you're allowed notes, then you might not choose to actually get the derivative unless they say you have to do it algebraically. You might choose to write down that the maximum is at t equals 1 on b, and the y value, or whatever the context is, you'd sub 1 on b back in the function to find the actual maximum value. That might be easier than differentiating. So look for that. You are allowed, if you're allowed to take in notes, you could note that down. And similarly, the point of inflection is even more difficult, isn't it? The point of inflection, when the function is decreasing at an increasing rate here, and then decreasing at a decreasing rate. Okay, that's a point of inflection, change of curvature, and that is the second derivative is equal to naught. Oh, you might not want to find the second derivative of a function like this unless they make you. They say show algebraically, you have to do it. But otherwise, you might just note down on your notes that the point of inflection is at t equals 2 on B, actually twice the value of the maximum point, isn't it? And the y value, or whatever the context is 2a over BE squared. You could write that down rather than try to work with the actual function algebraically and get the second derivative. So I think you should make those notes now, because this is typical of a surge function. Obviously, in any given context, you need to feed in your particular A's and B's there. Okay, so this is an interesting one. Are you getting excited about this? You can see some really important applications happening here. And I'd encourage you to do some of the maths here, to just prove that the point of inflection is that. Okay, and just keeping in mind now, I just want to make a bit more of a deal about this point of inflection, because the point of inflection, of course, is the maximum or minimum rate of change. So in this one, the rate of change here is dy by dx, and it is its most negative. It is decreasing at its fastest rate. So that's a minimum derivative here. And you could do that on your calculator. You could store up a particular surge function. I'll talk about this later. And its derivative, and see that its derivative actually is a minimum at this point. It's the most negative rate of change or slope of the tangent that you get. So just keep all of that old stuff with graphs in the back of your mind there. Okay, so let's go down and have a look at another function. Here's one here, the logistic function. Oh, that looks complicated. Still got the basics of the exponential in there. That's a negative. I just messed that up. So let's just go back. That's e to the neg bt. And how does that graph? Well, look at it here. It's approaching, the important value is this plateau here. It is plateauing in its growth. It's a plateau. And when drawing this, generally you would make this a dashed line to indicate that you can't have that value. And make sure, if they ask you to draw a graph, that the arrow doesn't touch that line, because it only approaches that value. Let's have a look at the maths of that. If you write this function out over here, and you want t to go on very large, then e to the neg bt is 1 over e to the bt. If t is getting large, this is going to tend to 0 as t tends to infinity. So this whole thing here, e to the neg bt, is going to tend to naught, so y is going to tend to c over 1 plus naught. It's going to tend to c. But it's only tending to. This can never be 0, can it? It'll never disappear. So it will get closer and closer to c, but actually can't equal c. Okay, because this is only tending to 0, this e to bt. Alright, so this is an application in biology. The logistical model is used for the growth of populations limited by resources. So it plateaus due to limiting resources. And that's why it's called the logistical function or logistic function. Because it's not practical to have a function always just increasing. There's it. We've got here, let's say that's a population. That's the first part of the function in here. But then it go on forever? I mentioned this in the last part. No, nothing goes on forever like that. Resources are going to run out, or predators are going to come in. It would be rare to see an exponential increase going on like that forever. So what's the practical or logistical adaptation of that? Using the idea that logistical means the practical aspects of a problem. What are the logistics of that? What's a practical context and a situation that we have to bring to that? Well, that's where we use this function. It's the made practical, if you like, the exponential growth, so that it over a long period of time describes what's really going to go on in practice. Okay, so again, this is a very, very important function. So let's tidy this up and just say again, if you're asked for, let's say, when is the population increasing at the greatest rate, right? Rate of change is the derivative, dy by dt, and you want that to be a maximum. So that's at that point, and that's when the second derivative equals naught. Do you really want to differentiate this thing twice? Have a look at it. In some of the exercise they ask you to have a go. That's fair enough, but if in any test or examination you're allowed notes and they don't ask you to show algebraically, what I'd suggest you do is write this down. And then for your particular function, of course, there'd be a particular A, particular B, particular C. And use that. They just say find when the rate of change is the greatest. So this is a maximum here, isn't it? Point of inflection, getting the rate of change, the slope of the tangent. Remember the trichotomy there. It's getting greatest there and increasing at an increasing rate. Then it's increasing at a decreasing rate. So that's a point of inflection. And so that's when the rate of change, dy by dx, is a maximum, second derivative is naught. So rather than use algebra, maybe just write that down. Okay, and it's useful to see that it's halfway up to the plateau, C on 2. And you might remember the y-intercept or the dependent variable intercept, because it's usually going to be something like population, that is C over 1 plus A, but rather than have to work it out each time. Okay, and that's only if they say you're allowed to, that is, they don't ask you to prove it algebraically. Alright, so what we're going to do now in this first section is not actually model data, but we're going to use these models to try and answer questions here. And so here we are here. Let's have a look at this one. This is a surge function now, administering a drug. Draw a sketch of the graph. So you'll use technology there. The important thing, though, is when you draw this graph, remember what the marks are for. Let's say, this is E, so we'll have an E up here. And this is time. You should have a labelled scale, time in hours, so 1, 2, don't just put the dashes, you have to label that and put down the units, hours, and then up here as well, in hundreds or whatever you're going to do, you have to make that choice. You look at the calculator, you have to have a scale labelled there, and the units, just there we'll put E units because the problem doesn't actually say what the units are. And so we have to have that. Now all of that is worth 1 mark. Then you have to have the key features and good shape. Oops, and that's not a good shape. So let's try and mark this. So where does a surge function start? It always starts at 0 and coming in like that. So the key points is that's got to be right. That's got to be right, and this decline here, this is a bit shaky, should be about right. Whatever that point of inflection is should read off pretty accurately. That's 1 mark, and then we want a general shape mark. So 3 marks for something like that. So you really do need to pay attention to that. So we have to go back up. I think we have to go back up and have a look at, not that far though, we just come down here and have a look at here. Can you see the surge function, because of that t is 0, starts at 0, and have a look at its shape. And then down here in this one, this doesn't start at 0, so just check those key points there as you draw yours from the calculator. Okay, so this is very important. Too many students just rush a shape off a couple of axes. It's got to be far more detailed than that. You've got to show that you understand what the calculator or technology is producing. Okay, I think you can do this problem pretty well. Just notice here, find t at the point of inflection of the graph. That can be done with the formulas that I was talking about before. If you are not asked to find the second derivative or do it algebraically, then you'd use the formulas. There is another way of doing that, of course. You could put that you could put the derivative on your calculator, and we might talk about that a little bit later on. But at this stage, probably use the formula there. All right, so I'll leave you to try those few problems there. I'll scroll down so you can have a look at the others, and just practice your graph drawing here. Okay, so pause the presentation, have a go. We'll go down now to 4, 5 and 6. Remember, the answers are coming up underneath. So here's a big problem. This is a logistic problem asking you to prove that point I said, the point of inflection. Have a go. If you're any good, you might be able to do it, but it's pretty tough getting that second derivative of that function. I'll give you a few hints in here, so see how you go. Okay, that's 4, 5 and 6. Question 7 is an important question. To have a look at why the model is not acceptable. Okay, they put some tempting little plots in there, and they look as if they're certain things, but what's wrong with them? Is there something wrong with them? Okay, so that's honing up your skills on understanding the various functions. They might particularly look at where, when t equals 0, is the starting point about right? And then look at the other properties of the functions and whether the data is showing those properties. All right, so have a look at 7, that's A, B, C, D. Let's come down now. We'll bring these E, F, G, H. Okay. So pause the presentation and have a go. And then here are the answers. Question 1. We'll try and get question 2 and 3 in there. Okay, we'll just do the rest of question 3 now. Okay, into question 4 and 5. Fit those on there. The rest of question 5 there. Okay, question 6. That's the biggie. Fairly difficult differentiations there. And question 7. All right. You toggle backwards and forwards and mark your work. Let's move on now. Okay, so now what we're going to do is actually very similar to how we were looking at in the last presentation, that bacteria experiment. So we're going to go out and get some data points. These are 2 examples here. And going to put them on the calculator and first of all have a look at the graph and then get the calculator to suggest a model. The calculator uses a method of least squares regression to actually fit a curve. And what that means is it's going to minimise the squares of the deviations away from the model. In other words, put a line through the points which minimises the sums of the squares of the deviations from the model. It's the squares, of course, because you could have deviations that cancel each other out. One above the line and one below the line end up with a perfect fit with none of the points on the line, perhaps. So it's going to actually fit a model or a curve which minimises the sums of the squares of the deviations from the model. It's called least squares regression. Not part of this course. Okay, so what are we going to do? Come down here and have a look at all this calculator work I've got for you. But first of all, come over here, we have to choose stat mode. That then gives us this window, and into list 1 we would put the independent variable, and into list 2 the dependent variable. Okay, so usually, as we've said quite often, the independent variable in contextual work is time, and then the dependent variable could be population or drug content, etc. in our surge examples. Okay, so if you do that, we then need to hit graph here by going to F1, and we now get this window, and if you hit then set or get set by hitting F6, we get this window. Now it's very, very important that we define stat graph 1, so we're going to define stat graph 1 and draw that in a minute. So stat graph 1, we could do graph 2 or graph 3, but let's just put in graph 1 whole there. So first of all, we want to make sure it's a scatter graph. Okay, so if it's not, we've got to scroll down with this button here and then choose a graph type, and then list 1 and list 2. Choosing xlist, so this is the independent variable, usually in list 1, xlist, and dependent variable. That's what we would do mathematically. Always have the independent variable on the x-axis. Okay, so once we've done that, we can hit execute, and we'll just come down screen a little bit here, and if we hit execute, we're back to this window, which then we're going to hit graph 1. We've set it up so that's hitting F1, and we get this graph. Okay, so what do we want to do? We want to basically draw the best fit curve through here. So we're going to ask the calculator to calculate. So we hit F1 and we get this window here. Alright, so this gives us a choice of what sort of model we want to try and fit. Well, none of these listed under here are suitable. We think this is exponential, let's say. So we want to choose the next window. So you hit F6 and we get some more options here. And obviously exponential is what we think it is. So we'll hit F3, and when you hit F3 it'll fit an exponential. So what are we going to choose? Well, we'll choose E. Why would we choose E? Well, choose E. You should be very choosy about choosing E. And the reason for that is about its derivative, isn't it? That excitement from the last presentation. So we're going to try and fit a function of the form ae to bx. So you're going to choose F1, and there it shows you. There's a formula for the function with an a value of 20.155. You usually use 3 significant figures, or maybe 4, and then round off your answers correct to 3. There's the b value, and we can put our final function in. And it's got a high r and r squared. We don't discuss that much in this course. This is a measure of the, particularly r squared is a coefficient of determination. It gives you the percentage variation in one of the variables in the dependent variable attributable to the variation in the independent variable. How much the variations are connected, if you like. Coefficient of determination. Okay, so here we're going to draw the function, so hit F6 or just execute, and there we have it. And it looks like a pretty good fit here. Okay, we might like to be able to work out values in between here, maybe. So we can do something there. If we exit that and go back to this window, I think we've actually got to go back and redraw the function, then you might hit copy. Have you done this before? Hit copy by hitting F5, and the window that comes up then is this one. It goes back to graph mode. What you're doing is copying this function into graph mode. So it'll go to graph mode momentarily, and then if you hit execute from this screen, hit execute, then it comes back to this one. But what's happened, if you then go to menu and graph mode and check that hole again, you'll find your function is in there. Your function has been entered in there. What's the value of this? What are we doing? Well, if you then hit draw from F6, you now have in graph mode your function fitted from stat mode. What's the advantage? Well, here it is here. Oh, Gsolve. Because what that means is you can find any x values or y values along that curve, or maximum, minimum points, and so on. Because Gsolve's on board and is only applied when you're in graph mode. So that's the value of copying something across from stat mode into graph. So that's handy, because if you're not asked to show something, you can just use technology and Gsolve here to find an x value, a particular y value, and so on, using xcalc and ycalc from Gsolve. So keep that in mind there. All right, so bringing your technology up to date there. So let's go on with the next type of function using technology. Now this is an interesting one, because the surge, let's say we get a set of data points like these that look to be described best by a surge function. Now you can see the calculator or technology's got a problem here. There are two places in that formula on the right hand side, that explicit formula in T with that independent variable. Now you might just have looked back, and in defining your graph, x list, list 1, y list, we're in trouble. Can you see it? There's no two places, if you like, there you put the x number in list 1, the y number in list 2, and you're trying to fit a curve. But hang on, the formula's got two positions over here. This is going to be difficult for the calculator to have a plot of one variable against another. Okay, so here's what Hayes and Harris are suggesting. Plot T and Y on T. Let's have a look. Let's see why that happens, why that's useful. Well, if I divide both sides by T, Y on T equals AE to the neg BT. So if I plot that as my new Y value, if you like, then what am I going to get? So I'll put into list 1 the independent variable, put this into list 2, and the calculator only now has to work out a basic exponential function connecting y and t. Then when I get that, I can say, well, that means y over t equals whatever function they have gotten for me from the calculator, and then multiply it across again. So that's the idea. So we will actually use that in list 1, and in list 2, well, no, we'll put it in list 3, because in list 2 we've got y, okay, from before. Let's do it. Let's come down here and see what we're doing. So here, we'll just go back up again. So here, let's come down there. Okay, so here, there's our original data, t, and this is y, or whatever the context was. And then, what do we do? Well, with this button here, we move our highlight up to list 3, because we're going to tell the calculator not to use y against t, because it's got the surge function's got 2 places in the formula with the independent variable. We've got to make it easier for the calculator than that. So into list 3, when it's in that mode, we want to enter a formula telling the calculator to put into list 3, come up here, we want y over t, which is list 2 values over list 1 values, aren't we? That's what we decided to do. So here, how do you put a list in there? So this is highlighted, then you go to shift, here it is, shift, and then you've got to find list down the bottom and put in the list. So list down the bottom is shift key 1, put list there, and then we can enter 2, and so come to this window, we've got list 2, and then divided by, so back on here, divided by, and we'll just scrub that out, I'm not showing the divided by sign there. So divided by, and then do it again, and put in list 1. So just watch this window here, down in that hole there, shift 1 gives you the ability to refer to another list. So if you then execute that, what pops up in list 3 are list 2 values divided by list 1, which, if you like, is your big new y, which you're going to find a formula connecting that to t. So now you would have to put the, let's go to setting it up for, let's say, graph 2. So the x list would still be list 1. The y list is the big y, y over t, would be list 3. And then you would have just a, this is big y, y over t, and you're going to have an exponential like this, which you can get the formula for and then multiply across by t. That's the idea. We've got to simplify this function for technology. All right, so you will get a chance to play with that in a minute. What about this one? This again is a complicated one. If we get a set of data points here that look like that, then you say, gee, I think this is a logistic function. So you go to your calculator and see if you could fit it. So we'd have the same thing here as before. This would be in stat mode, list 1 and list 2 again. We draw the graph there, and well, this doesn't look, I haven't actually done enough of this, but let's imagine we're trying to fit a logistic model to it. Then there's no logistic option on that page. So go to the next page, there's no logistic option on that page, but on the very, very last page, there it is, logistic. And if we hit execute there, it would fit a logistic model. Just note here, I haven't got enough data to actually warrant a logistic model because it should be plateauing, shouldn't it? All right, so the logistic model is on the last page of our modelling options there on the calculator windows. All right. Do you feel confident? We'll give you some data then and see if you can model some stuff now. So here's an example. Let's have a look at what Hayes and House have got here. Strawberry plants are sprayed with pesticide fertiliser mix. So here we are. And what is it going to be? They're suggesting the independent variable be called X mils of spray and yield per plant Y strawberries. Okay. and the X mils is per litre of water. That's a concentration. I must admit, in this modelling, I would rather you used S and big Y. They put it as X and Y there so that the student gets the variables in the right place, because clearly the spray concentration is the independent variable and the strawberry yield is going to result from that. It is the dependent variable. So this has to be on the x-axis and this is on the y-axis in technology land. But I still would rather see it as yield. Confusing there though, that becomes y, doesn't it, if you look at the letter, and the spray concentration in millilitres per litre of water, and the yield is in just strawberries, numbers of strawberries. So, oops, and I've done it the wrong way around. Okay, let's get that right. So here, I just got through saying what's on the y-axis is the yield and the spray concentration down here, millilitres per litre, and the yield is just the numbers. Okay, so that's what we're trying to do. You always put the independent variable down on the x-axis. All right, generate a scatter plot. Okay, so there's the scatter plot, and suggest a suitable model. You don't actually have to draw the graph, and it looks like a simple exponential growth model. So then you get the calculator to find the model as we did before, stat mode on the calculator, producing the plot, then to set up graph 1 or graph 2. Graph 1, go to calc and choose a model, and if it's exponential it's on the second window, and then come up with it, and the calculator will plot it over the top of the data and predict the average number of strawberries per pound. The spray concentration is 3 mils. Now let's have a look. 3 is in between here, so that's called interpolation, isn't it? It's interpolation because you're estimating points within the data set. So they haven't asked here, is it a very good estimate? But it would be, wouldn't it? The fit is quite good of the curve. It's interpolation between points that have been modelled pretty accurately. So we'd say this is going to be quite accurate for those reasons. They don't ask that here. And when x is 3, y is approximately 13.8. Now, how would you do that? This is a prime example of how you could get by without algebra. So here, y is approximately 8.023. So they're using 4 significant figures, so we can round off to 3 in any final answer. We would put in 3 in there, and you could work that out and round it off to 3 significant figures. So you'd probably say, actually contextually you wouldn't say 13.8. That is approximately 14 strawberries. In this course we want a practical answer here. So 13.8 should be rounded to 14. But if they don't say, and they don't here, that you have to substitute in like this, you could have copied across to graph, particularly if you've got more than one estimate to do, copy across to graph and use gsolve. And this would be a y-calc for an x equal to 3. So that could be useful. I mean, this calculation is not that hard to do, just in run mode. Okay, so, but if you wanted to do more work with your modelled function, copy it across into graph and draw the graph and use gsolve. Okay, how do you feel about that? Okay, let's have a look at some then. And here we have one here. Mass B grams of bacteria. So here again, defining the variables, mass of bacteria, B grams, and so on, and then asking you to fit a model to the data using the calculator. Use the model to predict the mass of the culture after 3.5 days and 10 days. Is your answer to D part 1 likely to be accurate? Well, so this is about interpolation, going past 8 days. What would your comment be? Extrapolation, bit doubtful. Okay, remember all that stuff. And so you might do this by actual calculation. And I'd say plus, copy to graph, copy the function across to graph, and check your answer with GSOL. So you're flexible there. It doesn't actually ask you here how well the model fits, but it might be worthwhile, and we'll perhaps see that later on, to discuss the fit. So I'll get you to do these problems, then come back and we'll have a little section on what you thought about whether the model fitted. Okay, so have a go at these questions 1 and 2. And pause presentation. I'll, as usual, just go on now. Okay, so here we have sample 15. Now, I've put the answers right at the end, so we'll go through and you can toggle forward to get them when we've done these half a dozen. Okay, so here pain-killing injection and suggests a possible model. Well, you can see here it looks like a surge model, so you can't fit that directly. So you plot E over T against T, use exponential modelling. Now the important thing here, and I didn't mention that before, 0, 0 here has to be excluded. So just notice that there. You can't have in the X list, you can't have 0 because you're going to be dividing by that X list values, list 1 values. So you have to delete that for this surge modelling there. Okay, so what are you going to do? You plot list 3 as, or you enter list 3 as list 2 over list 1, and then list 1 is X list and list 3 is Y list, and you can come up with a model here. Usually 4 figures, so that answers can be rounded to 3. At the end. Okay, so having a look at the fit of this model, there it is, and then we say, well, when is the drug at its most effective stage? That's its maximum. So now to find this maximum, combine dE by dt, or use technology, or use your property, remember, of the surge function. So I think this is the easiest way, right? If you're allowed to, if they don't say show that. So that's the number 1 preference, just 1 on B. And what's your B here? B is the number there, not the negative part of it. 1 on B, which is 1 on 3.147. Technology would be copy to graph and use GSOLV. And then the hardest way of all is finding the actual derivative. So 1, 2, 3 in that order. Okay, so 3 only done if they ask for show that the maximum is, or algebraically, something like that. Show algebraically or find algebraically. Otherwise you'll use those other 2 methods as a preference here. Now, the last part here, if the operation cannot commence before the effectiveness reaches 60 units, after what time can the operation commence? So we want to know when E is 60. So you put 60, I haven't shown this, equal to 804.5 T to the negative 3.147 T. You're actually going to have to solve that using what they've suggested, technology here. Yep, well, that would mean you go across to graph mode where you've copied the function in, and you find the xcalc for a y of 60, and you come up with that 0.103 hours or 0.721, so 6 minutes, 43 minutes, round off to the nearest minute, make it contextual. So the operation can start after 6 minutes and can last 33 minutes, or go to 43 minutes, which is 37 minutes difference between the two. So that's an interesting question. Yes, it's important there to have that technology, I think, on board in that one. I mean, you could try to solve something like this, find the value of t for which e is 60. All right, well, I've actually left out there, I think, the t in there. T, yeah, so t is that. So that's you can't actually do that algebraically, that one. You need to have that copied across in graph mode. All right, well, let's have a look at this one a little bit differently. So I'll just scrub this out here and have a look at an aspect of this one, because we can see something about the model here. Does the model fit? And sometimes they ask this. So first of all, why would you say it was a reasonable fit or not? Number one, why have you chosen a surge model? The points display the characteristics. I'll just get this right. Characteristics of a surge function, right? So that is starts at 0, has a maximum, or quickly reaches a maximum. Let's put that. Let's just put that. So quickly reaches a max, and then declines and tends to 0. So that would be one reason. The points, what? Most points are close to the model. Most data points are close to the model. And part 3, well, it's not very good here. These are not randomly distributed. We'd usually say the points are randomly distributed about the model, about the graph or the model. Not very well here, so this isn't a really good fit here because of that circled bit I've got up here. So it's not a bad fit, but we could have the points closer to the line there and more randomly distributed. So that would be the sort of thing you would need to talk about with any function if the question was comment on the fit or comment on why you've used a surge function here. All right, let's go and do some. So here's questions 3 and 4, and going to have to work out for yourself from the shape of the graph what you're going to try and fit here. And you'll see that quite obviously, and I think there come another couple of surges in that one. All right, so let's go down. The next example here, and it's a bacterial problem here. Draw a scatter graph, find the model. Okay, so here we have the bacteria are actually plateauing here in number, and so what they might be with bacteria limiting resources, but with bacteria there's another interesting thing. It might not be they're running out of nutrients, there is something called contact inhibition, where if the cell walls of bacteria are in close proximity, that contact inhibits the growth. So that's interesting. That's another reason why it's likely to plateau over here. All right, so a logistic model is suggested. They're not asking why here. So you could say the pattern of the points, it starts at a low value, rapidly increases and then plateaus, the characteristics of that graph. And to say then, right, well, is it a good fit? Well, we could comment on it from down here. Yes, most points on the line in this case, and the others are randomly distributed, something like that. So it's quite clearly a good model. So here we would write the model down straight off of the calculator, and we're going to use 4 figures. So we can round to 3 significant figures in any of our answers. So then estimating the bacteria these times, so we could put those times in, either in run mode, that's going to be a bit long. You'll go to copy and put it into graph and draw the graph there and use gsolve to do a y-calc for those 2 x values. Estimate the initial weight of bacteria added to the milk. So it's 0, so we could put T as 0 in, or again using gsolve if we've copied that across. And then at what rate is the weight of bacteria increasing after 6 hours? After 6 hours, well, we need the derivative at T equals 6. So what's the easiest way of doing that? Well, I think there they don't give you any idea, but what you might do is when you've got graph mode, here we are, and it's been copied across to F1 in graph mode, what you can do, you've got your function now, this is T and B, and you could actually go to F2 and enter the derivative of F1. So you could actually enter the derivative and draw it. So it goes like this, the derivative of that logistic function, and find the value at T equals 6. So we could just draw that and gsolve for that, because you probably don't want to actually find the derivative of this thing. Okay, so at T equals 6 we would have dB by T as that. And then at what time does the rate of growth change from increasing at an increasing rate to increasing at a decreasing rate? That's the point of inflection. And that's what they've got there, and you would use your formula approach for that. Okay, so you'd use the formula for the point of inflection in here, ln A on B, that sort of thing, C on 2. So have that written down so that you can use that for that point of inflection. That's the point in here, of course. Those 2 points. All right, so have a go at that. I think you probably need to look back at your calculator usage here to get the value of the derivative at T equals 6 to make sure you can enter into F2 dy by dx, which just remembering there, if you go options and calc, you will find d by dx and d2 by dx, etc. are options there. So entering that into F2, d by dx and then y1. And this really should be not function 1, Casio, it's y1, and then into y2, put d by dx of y1. Okay, so you might have a go at that. All right, let's have a look at doing some with that and then have a look at some answers. Okay, here we are, and again this is going to be a rumour spreading around, is going to spread rapidly and then plateau, so this is likely to be logistic, and so is this. So have a look and see what you think, remembering to use technology wherever possible. Okay, let's go down now and look at all the answers. Okay, so here's question 1. Question 2. Question 3. And we'll just make sure we've got question 4 there. Question 5. And question 6. All right, let's finish off now with some interesting points. Applications of exponential and log functions. So we really need to be able to do the whole range of things we do with derivatives, tangents and normals, rates of change, curve properties, applications, optimization, find maximum minima in an applied sense, all of those things. So it's very, very important that you can apply all of this. Now, what we're going to be doing is working with a number of common functions, and so I think it's not a bad idea to, for exam and test purposes, to actually go down to Y10 on the Casio, so leave Y1 to Y9 available for other use, and enter a function, and I would say put in a typical surge, and then so what might that be? Y equals, I don't know, 20t e to the neg 0.2t or something, and then its derivative, d by dx of y10, and then in y12 and y13 choose some logistic function and its derivative. So you've got one in there, typical, so that if you're given one, it will be different from this one. You just go in and edit it, edit those numbers, and you've got the derivative underneath it for future use. That's useful. And then maybe, what else can we say? Y14 and Y15, you might choose to put a log function or a limiting value function in there, or keep going with pairs of functions. We're going to have a look at these, what examples of all of these in practice. But this isn't a bad trick for improving exam performance, to have examples of them in there which you will just edit if you get another function like that. Let's come down and have a look at this. So the first one here is find the equation of the tangent to y equals ln x at the point when y equals neg 1. So here, first of all, when y equals neg 1, ln x is neg 1. Okay, therefore you can solve for that. If the log of a number is neg 1, that's the power of e. So it's 1 on e. So the point is 1 on e neg 1. How do you find the slope of the tangent? You need the derivative. So that's 1 on x. You then sub in the x value of the point and you get the slope of the tangent. Then using this method, take the y value of a known point on the line over x take the x value equals the slope. That's what they're doing there. And then multiplying across and simplifying. Okay, so that's using just the basic idea of tangents for this first one. So there's a few there. all just basic functions, I think. Yep, not too bad. I would do a few of these, some of the harder ones perhaps, maybe 2 and 3, normal, question 4, no, question 6, and choose a few more perhaps. Let's go down and have a look at a few more. These are basic functions back from your previous study. You can have a go at them, but we're really interested in more complicated functions. So maybe we do this a bit different. Question 9, maybe question 10. Now you do all of them would be ideal if you've got the time there. Question 11 perhaps. I think question 12 is important. Here's a log function. So this is one that you might put and store in your calculator with its derivative underneath. An example of a log function, something like that. So you can doctor it. If they give you a log function in a test or exam, just edit it out rather than having to enter the whole thing. Question 13, probably have a go at that. Question 14 is interesting. We keep going. Do all of them if you have the time. That would be good. Here's question 15, 16. Interesting questions. Hang on, we'll just go back up there. 15 and 16. I think probably this is an interesting one, a limiting value function there. Question 18, could have a go at that one. 19, yeah, well 20 is quite a challenging problem. It's a distribution function. You know, in statistics, the probability of getting a person of height greater than 200 centimetres. That's a normal distribution curve. Alright, a formula for that, so you could play with that. 21, 22. I think 22 is pretty important. They like graphs and things in tests, so that's an important one. Revenue problem. Yes, quite interesting. This one, 24, a harder problem. We'll go at that. And probably both of these would be worth having a go at. Okay. Toggle back, start your work, and let's have a look at the answers down below now. There's question 1 to 3. Question 4. Question 5. We'll look at question 6 then. Let's just come back. Yep. Come back here, question 6. Question 7. Question 8. Question 9 and part of 10 there. Right, there's the whole of 10. Question 11. Question 12. Looks like I've got that one there twice for you. Thirteen is doubled up as well. Question 14. Question 15. Just go up here, question 16 and 17. '18 and 19. '20. '21 and 22. '23 there. 24. And 25 and 26. All right, well, you've got some skills now, you must admit. That's fairly challenging work, and I hope you're excited about that now, because it's using calculus in a very practical way, and some exciting modelling there. Well, that's all for this presentation now. I hope to catch you in the next presentation. Cheers for now.